Hello everyone, this is Nash. Today I would like to introduce you the physics and mathematics of an RC circuit. This is a circuit basically connect with a resistor and a capacitor, and I want to use a battery. I want to use a battery to charge my capacitor. I'll first try to discuss the RC circuit to analyze the whole circuit simply by physics. And secondly, I want to find out the exact answer, exact function, maybe function for current, maybe function for charge, simply by doing a little bit calculus. So let's get started. As you can see, there are three components on my circuit: your battery, your resistor, and your capacitor. And when I close the switch, I complete the circuit. So your charge is going to try to push, your battery is going to try to push the charge out of the battery and cause the current flow. And this is the traditional current. So first I want to simply introduce the voltage. The voltage marked on your battery, for example, might be 3 volts, and that means when 1 coulomb of charge try to pass through your battery, it will carry 3 joules of energy and start to travel outside the circuit. Okay, so when your current carry the energy and start to travel outside the circuit, the first stop is going to meet your resistor. And when your current try to pass through your resistor, the resistor is going to change your potential energy to be heat energy and then radiate it to the atmosphere. So that will cause a drop of your potential. And your current keep flowing, and finally, eventually, we end up stored on the capacitor like this. On the upper plates, it is positive charge, and downward plates is the negative charge. And try to imagine, usually the positive and negative charge will like to attract each other, and however, you're not trying to separate them for a finite distance, and that means you need to do work. You need to do work to those charge. So this is how your capacitor built its own potential difference, built its own electric field. Okay, actually it is the electric field generated by those positive and negative charge and then creates the potential difference. Okay, and now you can try to imagine, as more and more charge is now accumulating on both plates, it creates electric field and potential difference. So your capacitor is going to act like another EMF device and try to push the charge back to the original battery. Okay, so you can imagine that the current I will not be simply a fixed value. It should be a function. It should be a function of time. And how do we define the current? The current is actually how fast your charge is now moving. So to be more specific, your current I is dq by dt. So you can imagine, if your current is not a fixed value, it is a function of time, and that means your charge stored on the capacitor would also be a function of time. So I want to find out the exact answer for the function, for the charge function, and for the current as a function of time. If I could find out the 2 answers, and that would be awesome, because one day if I want to know what the current might be at some time t, I just need to plug in t into the equation, and I can find out the exact value for the current and the charge. Okay, so this is the first part about the introduction to physics, and the second part is one day your capacitor is going to be fully charged. And the potential difference across your plates, if I were to say connect a voltmeter across your capacitor, then I can read the voltage, and the voltage is the potential difference across your plates. And one day when the potential difference across your plates is equal to that of the batteries, then there's no more current. Your current is going to stop, simply be zero. Because think about it, you now have two batteries that are trying to fight, and is now fighting against each other. And when they got the same power, when the VC is equal to VB, no more current will flow. The current will simply be zero. So you can expect that at time equals zero, at the beginning, you might have the maximum value for your current I. When your capacitor store no charge on it, you might have the maximum value for current I. Okay. So since if I let time goes very long enough, let's say it goes to infinity, your capacitor is going to be fully charged. And how will I determine the time? How can I determine the time? And what are those key factors that will influence the results? In order to answer this question, you need to think like a physicist without doing any math, any calculus. I will suggest you can first think of your capacitor as a reservoir. What does it mean? Just before your imagination, first I need to introduce you what is the capacitance. The capacitance is actually defined as the charge stored on the plates divided by the potential bit by those charge. This is how I define the capacitance. So actually it's also an indication. It indicates that how much charge your capacitor can ever store for a given battery. Okay, so you can think of your capacitor just like a reservoir, and you're trying to fill it up. Your capacitor, fill it up, your reservoir. If you now increase the volume of your reservoir, you definitely will need more time to fill it up. Okay, so if I increase C value, that means I should take longer time to charge my capacitor. Okay, so in addition to the capacitor, in the RC circuit, there's also a resistor. So how will the R value, how will the resistance influence the time? Okay, now you try to imagine the connecting wire is a pipe, and your resistor is just like tiny rocks. You're not putting tiny rocks, so many tiny rocks inside the pipe, and you want to use that pipe to fill it up, your reservoir, and there's a flow of water inside the pipe. So if you try to increase the value, the R value, it's just like you're putting more rocks inside the pipe. That means you're now impeding the flow of water. In other words, you're now trying to slow down the flow of water. Okay, so if you increase the R value, you're going to increase more time to charge your capacitor. So now, just before I do any math, before I do any calculation, I can expect that the current in the circuit and the charge stored on the plates should be function of time. And secondly, if I want to charge my capacitor fully, and what would be the determining key parameters? What would be the key factors? And I find out that the capacitance and the resistance might be two determining important key factors. And at this stage, you might think, and what about the voltage for your battery? If I increase the voltage of my battery, will it be faster? Will it be faster to fully charge my capacitor? Possible, I don't know. So in order to answer this question, in order to find out the exact answers, I need to do some math. Okay, but just before I start to do a little bit of calculus, I need to first apply the Kirchhoff's law. You know, there are many different ways of pronouncing these names. Like for American English, they would like to pronounce it as Kirchhoff, or maybe Kirchhoff, but actually Kirchhoff is a German. So if you want to pronounce it in a more German style, you should pronounce it as Kirchhoff. Kirchhoff. And in my mother tongue, it is 克西赫夫定律. But if a pronunciation really bothers you, just forget about the name, just forget about the pronunciation. I'll just simply write it down as the loop rule. The loop rule. This is quite simpler and more direct. And the loop rule tells you that the potential difference across the terminals of your battery, and I'll write it down as VB, is equal to the sum of all the potential differences from each component. And you now get two components. One is your resistor and the other is your capacitor. So the VB is going to be equal to VR. That means the potential difference across your resistor, okay? And plus VC, the potential difference built by those positive and negative charge, okay? The potential difference across your capacitor. Quite simple. And actually, I would like to change this symbol to be E. What does it mean? This is epsilon. But the VB means the potential difference across the terminals of a battery. Okay, but if this is an ideal battery, that means I don't need to worry about the resistor inside the battery. When your battery is trying to do work to per coulomb of charge, try to push out the charge, and during that process, you don't need to worry about any wastage of energy. No energy will be transferred to heat during the whole process. So I can simply write it down as the E. And the E means the electromotive force. Or you can simply call it as the EMF, electromotive force. And the electromotive force is the highest potential difference that can be ever supplied by your battery. Okay, if we don't need to worry about the resistor inside the battery. Okay, I'll keep writing. Now the E is equal to VR. Let me help you review quickly. What is R? How do we define the resistance? The resistance is the potential difference across your resistor divided by the current passing through your resistor. This is how we define your resistance. So I can write the VR as I times R. And what about VC? Just like I said, your capacitance is defined as the Q over VC. As Q over VC is an indicates that how much charge you can hold under a given battery. So I can write the VC as Q divided by your capacitance. So I can change the VC to be Q over C. Is it okay? So just like what we expect that your current I and your charge Q should be a function of time. So your I and your Q, just like two variables, I would like to make them look more similar. So you can remember, how do we define the current I? The current I is basically how fast your charge is now moving. So it's simply dq by dt. So I can change the I to be dq by dt. So I can keep writing like this. The E is equal to dq by dt times R and plus Q divided by C. Is it okay right now? So far so good. Okay, let's keep doing the calculus. In order to do the integral, the trick is you need to separate the variables. You just want to put one variable on one side and the other variable on the other side. So now the q looks similar, right? You can take the q as one variable, and the other one is your t, your time t. So I need to simplify this a little bit. I first divide both sides by r. I want to divide both sides by r. So and that would be divide both sides by r, and I will just do a switch a little bit. E over r, divide both sides by r. This is q over rc, the q over rc, and I switch these terms to left hand side and switch them all. So they will be the e divided by r minus q divided by rc. Okay. Now I want to combine these two terms. So I need to give it a more similar denominator. So I'll simply multiply this term by c over c, and that will be the c over r times c. Okay, so for these two terms is now combining. So I can write it down as the rc and ce minus q. We're so close. Okay. Please let me remind you, our main goal is trying to find out the q as a function of time. I also want to find out the current as a function of time. So I want to put charge. I want to put this term. This charge is a function of time. I want to put it just simply on one side and put everything on the other side. Okay. So I'll just separate the t term and the q term to both sides. So what am I going to do? I'm going to switch the dt and the ce minus q. I'm going to switch them. Okay. So it will be, I can write it down right here. So that will be the 1 over rc times dt, and that will be equal to the dq divided by ce minus q. Okay, check it, let's check it. No problem. So far, so good. Okay, now I can keep writing. So actually, you're not capable of doing this integral since there is only one variable on the left hand side, and this is your time t. And on the right hand side, this is the q term. So I can start to do the integral. And for t, at time equals 0, I'm going to start at the beginning, and I will let's say we'll start at some time equals 0, and I'll integrate this term, integrate the t, the time, to some time t. And for your charge, since your capacitor starts uncharged, so there's no charge stored on the capacitor, so I will start at q equals 0 and to some charge q. So basically you can feel that your charge is now a function of time, and all you need to do is get this integral down. Then you can find out the equation. You can find out the function, the q function of time. Okay. So for the left hand side, it's much easy. It's much simple. It's simpler because you want to do the integral of dt. This is basically t. Evaluated from 0 to time t. This is actually this whole term. This whole integral is basically t. So I can write it down as t over rc, and that will be equal to this integral. Okay, this might be a little bit complicated. but don't worry. I just use a famous I call it a U-Substitution. A U-Substitution. I can let the U, I call it U-Substitution, U equals CE minus Q. And you do the differential, that will be the du is equal to minus dq. Why? Because your capacitance and your voltage for your battery, they're all constant. So the differential of your CE should be equal to 0. Okay, so I can change these terms. I can replace all these terms simply by my U-Substitution. So I can write it down. I replace the dq. I replace the dq by minus du, and I replace the CE minus Q simply by U. And I would like to remove the minus to be in front of the T over RC. So let's keep going. Oh, don't forget the limit. Since now I do the U-Substitution, so in order to be more convenient, I'll just write it down as I just write it down as f. That means I will do this integral from some kind of initial value to a final value. That doesn't matter. So if I try to do this integral, this is basically a natural log like this. And you're gonna do this integral, evaluate it from some initial value to a final value. But now, since you are not doing the U-Substitution, so you can replace the U back to the original form, like a CE minus Q. So I can keep writing as T over RC is now equal to natural log the CE minus Q, evaluated from some charge equals 0 to some charge Q. So now we're so close. We are close. You can start to plug in the 0 for Q and plug in the Q for Q. So let's keep moving. Okay, somebody might feel I might write it down too fast, so let me remind you a little bit. When you want to do the calculation about a logarithm, let me remind you a little bit. The natural log A minus natural log B, that will be equal to natural log A divided by B. So you plug in Q, and you get a term look like the natural log of CE minus Q and minus natural log CE minus 0. So this is how we write down this natural log CE minus Q over CE. Okay, so I need to remind you, the final goal is I want to find out the charge as a function of time, and we are so close. The Q, the charge, is right here, so I want to put it on left hand side and put everything on the other side. So let's keep right. Oh yeah, since I want to find out the equation, I want to find out the Q, I want to find out the charge, so I don't want to see the natural log. But how can I try to get rid of this natural log? So I need to use another tool, that is the e to the natural log x, and that will be equal to x. Okay, so let me do this to both sides, and that will be e to the minus t over rc is equal is equal, now I can get rid of this natural log. That will be equal to 1 minus Q over CE. Okay, we're so close. So now I'm ready to put Q on left hand side and put everything on the right hand side. So now I get the charge as a function of time, and that will be equal to CE times 1 minus E to the T divided by RC. Finally, this is the charge as a function of time. And that means if you want to find out the Q at some time t, you just simply need to plug in the t. If you want to find out the charge at time equals 3, you just need to plug in the t equals 3. Then you can get the charge at some specific time. Okay? And since your current I is also a function of times, and I is defined as dq by dt, so you can do the derivative of your charge with respect to time t, so you can get the current as a function of time too. So I can also write down my current I as a function of time. I'm going to do the derivative of this term, the whole term, with respect to time t. And since c is a constant, just forget about it. And if we want to do the derivative of the exponential term, since t is the variable, you can move the minus 1 over RC down and times the CE. Then you can cancel the C and leave the E divided by R. So I can write down your current I is E divided by R and times the E to the minus C over RC. Okay, this is the function for your current. The current as a function of time. So if you would like to graph these two functions, you want to graph the charge, you want to graph the current as a function of time, yes, of course I can do that. So let me plot this diagram for you. For the first graph, this is a charge as a function of time, and on the right hand side this is current as a function of time. Okay, so at time equals 0, think about it, at time equals 0, if your t is now 0, anything to the 0 power is 1, right? Anything to the 0 power is simply 1. So at time equals 0, this whole exponential term is 1, and 1 minus 1 equals 0. So that is what your capacitor is going to start uncharged. So I can graph the Q as a function of time t like this. It is going to enhance, increase, and then tapers off, and asymptotically approach some maximum value. Okay, and what about the current I? The current I, let's say at time equals 0, anything to the 0 power is 1. So at time equals 0, this whole term is 1. So you will get the maximum value for the current I, which is the E over R. So you can just simply write the E over R. The E over R is I naught. That means the maximum value for this circuit. So your current is going to drop at some maximum value and drop, and then approaches 0. So this is the two function for your charge and for your current I on the RC circuit. But however, I want to graph the last diagram for you, and that is the voltage, across the potential difference across your capacitor. So how do we define the capacitance? The capacitance is basically the Q divided by VC. So if I want to get the VC, I want to get the potential, the voltage of a capacitor as a function of time, I just need to find the Q as a function of time and divide your Q simply by C. So now I have the Q, so I can divide this whole term by C and cancel the C, cancel the C. So I can write down the voltage across your capacitor, I already done as VC, will be a function of time. So now the C is cancelled, so the rest part is the E times E minus E to the T over RC. So I can graph the voltage, I can graph the potential difference as a function of time, So let me tell you something. Actually, when T is equal to RC, this basically reveals something physical. It reveals something really physical because it tells you that how long you should take to fully charge a capacitor. And usually we call this T equals RC as tau. And this is time constant. We call it time constant. In my mother tongue, it's called 时间常数, the time constant. So let me graph the chart. Let me graph this voltage as a function of time for you. So let me introduce you and how to realize the physics meaning behind this time constant. Now, since the function for your voltage is quite similar to the charge, when T equals 0, this term is 1. 1 minus 1 equals 0. So your voltage is going to start from 0 and enhance and increase, tapers off and asymptotically approach the value of V. This will look like this. And when at time equals RC, when time equals RC, your VC is gonna be E times 1 minus E to the negative to the minus 1. And the E to the minus 1 is actually 0.37, so that will be the 0.63 times the E. And that means if you want to charge a capacitor, up to 63% of the maximum value, you should take a time equals RC. As time goes by, T equals RC, you can charge a capacitor up to 63% of the maximum value. So what else could the time constant tells us? And that means it is totally independent of the voltage from your battery. Remember, at the beginning, we tried to discuss the whole RC circuit simply by physics. We know that the C value, the R value, will be important key factors. They will influence the time if you want to charge a capacitor. And what we don't know is, I don't know how possibly could the charge of a battery influence the time. I don't know. But now I can be sure that if you want to charge a capacitor, fully charge a capacitor, this is totally independent, nothing to do with the voltage walk time of your battery, because your time constant is simply RC. It's decided by the resistance and the capacitance, and that means no matter what the voltage is for your battery, the voltage might be 1 volt, 10 volts, 100 volts, or even 1,000 volts. That doesn't matter. If you want to charge your capacitor up to 63% of the maximum value, it takes the same time. For example, if I now change your battery, I try to increase the voltage of a battery, and I write it down as the E1, and I want to charge it up to 63% of the maximum value. It should take the same time. At time equals RC. At time equals RC. Like this. Okay, and now increase. Okay, it will reach to the 63% of the maximum value at the same time, equals RC, and then tapers off and asymptotically approach the maximum value. So this is the physics that the time constant try to tell us. Okay, so if you want to increase the time for charging your capacitor, the only thing you can do is try to increase the R value, or the C value. You need to enhance your time constant. So what if I now increase the time constant maybe to some time constant is now R times some C with bigger value. Your time constant is now enhanced. But your battery is the same. So now if I want to charge my capacitor under this time constant to 63% of the maximum value, you would definitely need a longer time. Okay, and then tapers off and asymptotically approach the E. So this is the physics meaning for the time constant. If you want to fully charge a capacitor, the key factors is the resistance and the capacitance. And when when R times C, this is your time constant. It is decided by these two values, and it's totally independent of the battery. It doesn't matter what the voltage is of the battery. If you want to charge your capacitor up to 63% of the maximum value, if your time constant is the same, then it would take the same time. Okay, so this is the physics about RC circuit and some mathematics simply by doing a little bit calculus. Okay, of course, if you now remove the battery, if you try to remove the battery, and the charge to capacitor is going to act like another EMF device. It's just like another battery. So you would try to push the charge back to the resistor. It would trying to get rid of this charge stored on his plates. So how fast could your capacitor get rid of those charges stored on its plates? That is also decided by your time constant. So the time constant is just like the specific heat of an object. If the specific heat of an object is pretty low, and that means you can elevate its temperature or cool down the temperature quickly. Elevate it easily and cool down easily as well. So if the time constant is pretty low, and that means you can charge a capacitor as soon as possible. And also if the time constant is pretty low, you remove the battery and your capacitor is ready to discharge. Then you can get rid of those charges as fast as possible once if you get a low enough time constant. But I'll leave the discharging part for you, and compared with the charging process, the discharging part should be more easier for you, and trust me, you do need to practice. Okay, this is the physics and mathematics about the RC circuit for the charging process. Hope you enjoy it. See you next time. This is Nash.